Start. Okay, guys, once again, I welcome you to my lesson for today, where we'll be looking at mechanics. So this is just a continuation of the lesson that we started not so long ago. So remember, guys, previously what we're doing, we're discussing different types of forces, and we said, I still have that board. So the first type of a force that we looked at was gravitational force or weight, of which it is represented as a Fg. So the moment you see Fg, just know the force, or the F stands for force, G stands for gravity. So that means Fg is the gravitational force. Otherwise, we said gravitational force and weight is one and the same thing, and both of those are represented by a formula which says mg, with the m being a mass and then g being gravitational acceleration. Ladies and gentlemen, if I remember very well, we did discuss a little bit about normal force. So we said normal force is represented by a Fn. So the moment you see Fn, you know we are talking about normal force. Most importantly, guys, because it's a vector quantity, we make use of that arrow to indicate that this is a force which is a vector quantity which has both magnitude and direction. Very, very much important, ladies and gentlemen. So normal force, it's a vector quantity. So it doesn't matter the type of a force, but what matters the most is that we are focusing on a force. A force on its own, it's a vector quantity. So that means all of these are vector quantities. So these are just different types of forces. So remember, we said normal force is represented by Fn. Otherwise, you can just show that by writing capital letter N, with that arrow indicating that in this case we are dealing with a vector quantity. So can someone just remind me if on our previous lesson did we discuss frictional force, or we ended with frictional force? I'm just not sure if we did up to normal force or if we also discussed frictional force. Can someone just indicate? Now, I think we did up to normal force and we did not explain frictional force. So that is where we'll be starting on for today's lesson. Guys, can someone just confirm for me that part? I suppose the message is still sending. But anyway, it's fine. Whenever you get this message, you can just respond. So one thing for sure, I've just discovered that we discussed up to normal force. So in today's lesson, we'll be looking at frictional force. So guys, how do we represent frictional force? So frictional force is represented by capital letter F, then small letter f. Most importantly, an arrow at the top to indicate this is a vector quantity, or otherwise you can just write that f and then you indicate with an arrow. So in other words, this is capital letter F with small letter f, or capital letter F, small letter f with an arrow there. So those are two possible ways in which you can represent frictional force. So guys, I haven't got a response to my question, but can someone just indicate to me if I'm audible and again you are able to clearly see over there when I write? I just don't want to continue whereas none of you guys are able to clearly hear me when I speak, and again you find that you're also not able to see what I'm writing over there. Let me see who's on the line. Tando, Kevin, who else? I see Alberto. Are you guys able to hear me when I speak? And again, are you able to see over there when I write?
Yes,
Can
sir.
someone just indicate?
Yes.
Okay, 100%.
Yes,
So
sir.
now I'm going to confidently flow with today's lesson and explain. Remember, guys, in case if you've got a question, just make sure that immediately you unmute, mention your name, straight away. Ask your question, mute your mic. Don't wait for me to
Sir, your
respond
network.
when
Sir,
you need my attention. So someone is making a comment with regards to my network. So I'm not really sure if it's everyone who's struggling with the network, but you might find that wherever you are, there's a bit of an issue with the network. TK, Tando, make sure to mute your mic. If I mute it from my side, you will never be able to participate until the end of this lesson. So guys, I'm going to quickly continue with today's lesson. Ladies
sir,
and
the
gentlemen, we'll
network
be
is
talking
quite
more
slow.
about frictional force. So frictional force opposes
Sir, your
motion.
network is quite slow. Like,
Is it slow for everyone? Let me check. Kevin, Musas, Cindy, so how's my network on your side? I just want to check if it's mine or if it's for, who was it? Shreyas, how is it that side? Am I clear on your side?
Sir is good.
Yes, sir.
you are
Yes.
clear on my side, sir.
Okay, so this is an indication that in case if you are struggling with network, it could be yourself on your side. So you just need to make sure that you try different positions so that you catch network. Otherwise, it's fine. So guys, what I want to quickly explain is that frictional force opposes motion, full stop. With just that statement, ladies and gentlemen, it means if you've got your dream car there, it's in motion. It could be in that direction or in that direction, but let's just assume it's in that direction. So can you see, guys? Someone has got their mics unmuted. I am forced to mute it from my side, which means for the rest of this lesson, they won't be able to communicate. So, ladies and gentlemen, this is what I was saying. Frictional force opposes motion. Let me just write it down so that makes sense. Frictional force opposes motion. So this is your dream car, guys. It's in motion in that direction. In which direction? So we have west, we have north, we have east, we have south. Obviously, this is up, this is down, this is to the right, this is to the left. So frictional force always opposes motion. So that means if you want to know in which the frictional force is acting, you need to ask yourself this question: in which the object is in motion? In which direction is the object moving? So after you know in which direction the motion is moving, that's when you can say, okay, now that it's moving towards the right, that means the friction, it's in the opposite direction. Notice where I'm writing or I'm indicating that friction. Friction occurs between two objects. So this is the surface, or this is the ground, or this is the road. Then this is the first object. The second object is your dream car, which is in motion on that surface. So that means in between, that's where you've got frictional force, which opposes the motion. So it works against the movement of an object. Ladies and gentlemen, if you've got a parachute which is actually being launched in that direction, if there is a frictional force, it means it's acting in the opposite direction, which means it's going to be a frictional force in the downwards direction. Very, very much important, ladies and gentlemen. Guys, frictional force acts in the opposite direction to an object's motion or intended motion. Guys, very, very much important. The rougher the surface, the more the frictional force there is between the object and the surface. Listen to this very carefully, ladies and gentlemen. The rougher the surface, the more the frictional force there will be between the object and the surface. Musa, what does it mean? It simply means, in the opposite explanation, it means the less rough the surface, the less friction, the less the friction will be between the object and the surface. So remember, guys, we are doing physical sciences. This is a science which is physical. So obviously, if you've got someone, or let's say we've got a car traveling on the gravel in that direction, and you've got a car traveling on a smooth surface, which could be a tar road. Here comes the question, guys. Between car A and car B, which one is going to experience more frictional force? And what is the reason to that? Remember, mention your name, unmute, make your point, mute.
Kevin, car A, sir. The rougher the surface, the more frictional forces between the object and the surface.
100%. Ladies and gentlemen, in short, the rougher the surface, the more the frictional force. The less rough the surface, the less the frictional force between the object and the surface. Very, very much important, ladies and gentlemen. So now, if an object is at rest, then there is a static frictional force. Listen to these words very carefully, guys. In physical sciences, these words are very, very much important. An object at rest. So, the moment we talk about an object being at rest, then you know it means it's actually not moving. No motion, no movement. It's just nothing, guys. It's resting, it's at rest. So, if an object is at rest, then there is what we call a static frictional force. So this forms part of an additional information for you guys in grade 10 and again in grade 11. You just need to be aware that we've got what we call a static force, which is associated with objects which are at rest. And again, contrary to that, opposite to that, if the object is moving, then there is what we call, ladies and gentlemen, kinetic frictional force. Very, very much important, guys. So I'm still going to make use of those two diagrams to explain. Obviously, if an object is at rest, it means its velocity or speed is 0 meters per second. For argument's sake, let's say object B is moving in that direction at 300 meters per second. So that means this object is now in motion. What happens when an object is in motion? It means it's moving. Then this is where we have what we call, ladies and gentlemen, kinetic. I'll just write it down there so that for those who are writing notes, they'll just write it down. So there's what we call kinetic frictional force. In this case, we've got static frictional force. Obviously, the word itself, static, it's associated with objects which are at rest or not moving. Kinetic, we're looking at objects which are in motion. Guys, remember, there's this type of a sign which is called mu. What is mu, guys? Mu is it's a Greek letter which simply means mu. This is how you write mu. So this represents mu, ladies and gentlemen. Guys, what is a mu? What exactly is a mu? This is what we call the coefficient of friction, ladies and gentlemen. That's what we mean when we talk about mu. The coefficient of friction is what we call mu. So normally in grade 11, ladies and gentlemen, you need to be aware of what we call a mu. So obviously that if we have a letter being F, the coefficient is a number that is associated with that particular unknown variable or letter. For example, in mathematics, we know if we have x plus y, Shreyas, we know there's an invisible one over there, there's an invisible one over there. What do we call that one? We call it a coefficient. And this x or this letter is called a variable. Then at the top there, you've got a floating invisible one, which is the power. Very, very much important, ladies and gentlemen. So hence, coefficient of friction, which means when we want to represent what I've just explained in a form of a formula, that means you've got mu frictional force. So this is the coefficient of a frictional force, which could be any number. It could be 0,1, it could be 0,7, it could be 1, it could be any number. You just need to be aware that this is what we call mu, and this is what we call the coefficient of frictional force. Very, very much important, ladies and gentlemen. So, guys, the coefficient of friction depends on the material of the two surfaces that are in contact. Guys, let me make use of the same diagram to explain what I mean by that. Very, very much important, ladies and gentlemen, that at all times you listen very carefully to the physics terms which are being mentioned in this type of lessons. So I've mentioned multiple terms of which you just need to make note of those. I've sent information which has the physical terms and their description. So for every term that I mention of which you don't think you are aware of it or you're hearing it for the first time, just make sure to write it down. At the end of this lesson, you can just go through that information and browse through that specific term. It's in alphabetical order, so it's going to be easy to find that particular term. Ladies and gentlemen, the coefficient of friction depends on the material of two surfaces that are in contact. So in this case, we've got the car, which is the first material. Obviously, is the tire of the car which is in contact with the surface. So the surface is gravel and the tire is rubber. Ladies and gentlemen, in case B, we've got the rubber again, which is the tire in this case. But the surface here, it's not gravel, but is tar road. So that means a gravel and tar. These are two completely different materials. So you remember what I think it was Kevin, he said, the rougher the surface, more the frictional force. Very, very much important, ladies and gentlemen. So that is the reason why I'm saying the coefficient of friction depends on the material of two surfaces that are in contact. I'll give you some more examples, ladies and gentlemen. A still wet ice has a low coefficient of friction, therefore it slides easily. So just think of this as a cube of an ice. right? So this is an ice, ladies and gentlemen. It's just an ice cube. So on this ice cube, let's say we try to slide a steel. I'm not sure what it could be. It could be a razor blade, or otherwise it could be what is it? Whatever steel metal that you can use to slide on this ice. Here comes a question, guys. Do you think when we slide, let's say, a steel on that ice, it's going to slide easily when compared to a rubber sliding on a tar road? So let me just do it such that it looks a little bit more convincing. So in this case, we've got a tar and we are trying to slide a rubber, of which it could be, let's say, a wheel, or let's just say rubber. Here comes a question, guys. Between these two, which one do you think is going to slide easily?
A, sir.
A.
100%. So between A and B, A is going to slide easily. The reason is as explained. Guys, when an object moves along a surface inclined at an angle, the normal force is multiplied by the kinetic coefficient of friction to find the frictional force. Guys, I'm just going to quickly remove all of this and graphically or diagrammatically represent exactly what I'm talking about. Remember, guys, this lesson is being recorded. I'm going to post it on the upcoming days. I'm not really sure of the exact date, but just make sure that you stay until the end of this lesson because it's going to help you a lot. So it took me some time to prepare for this lesson. That's why I'm this much confident. I'm very much happy when you guys say the network is good on your side. So, ladies and gentlemen, when an object moves along a surface inclined at an angle, based on what I've said, I'm just simply talking about an inclined surface at an angle, and I mentioned an object moving along a surface which is inclined. So, guys, the normal force it's multiplied by the kinetic energy. What I'm saying now is that the normal force, which can be represented as capital letter N or otherwise as Fn, this is the normal force. So, what am I saying, guys? I'm saying the normal force is multiplied by the kinetic coefficient. Remember, kinetic coefficient, it's that one for a moving object, but static coefficient is for an object which is stationary. But in this case, I'm talking about an object which is sliding through an inclined surface. So that's why I'm saying we multiply by the kinetic coefficient. What is that, guys? What is the kinetic coefficient? Ladies and gentlemen, that is the mu. You remember, mentioned the mu. So because we specify this mu to say we are talking about kinetic mu, let's say mu k. So that is exactly what I'm talking about. So that means we also have mu s. What is mu s? It should be static kinetic coefficient. I mean static coefficient. So that is mu s. So now I'm talking about the kinetic coefficient. So this is mu k. That's basically what I'm saying, guys. I'm saying the normal force, which is that one or that one, is being multiplied by the kinetic coefficient of friction, which is that. Why do we have to multiply the normal force, guys? The main reason is for us to find the frictional force. That's it, guys. So we do that to find the frictional force. So that means we have frictional force as a result of the normal force being multiplied by the kinetic coefficient. So that is where frictional force comes from, ladies and gentlemen. So it depends on the material. So if the material is rougher or it's rough, that's where you are going to have friction. Depending on how rougher the material is, it's going to have a direct influence on the amount of frictional force. So that is why it's heavy to push a cart on a gravel as compared to when you push maybe a cart of the same weight on a floor which is tiled. So can you see? That means the frictional force there is going to be maybe, let's say, 20 Newton, but there it could be 7 Newton. So that is influenced by the material. So it's more like each and every material has got its own coefficient. So we just need to know what is the coefficient of this material. If maybe it's 0.7, that means we are going to multiply 0.7 by the normal force for us to get the frictional force. So let me also formulate that part so that it makes a perfect sense. But I'm just assuming that you've got an idea of what I'm talking about. So let's see, guys. Here comes a formula, a very important formula. Let's see. We have what is it? Frictional force as a result of normal force, guys. So the formula says force normal, which is a vector quantity. This is equals to force of gravity component being parallel. Remember, guys, we said we have a dot over there, and vertically downwards, we have what we call a frictional force, which is the weight. But remember, normal force is perpendicular to the surface. What does it mean when we say perpendicular? It means it's straight upwards, ladies and gentlemen. This is where we have a normal force, which is that normal force. So can you see? You have normal force acting at that angle. You have the weight acting at that angle. So for us to determine the force that is directly acting in the opposite direction with the normal force, we have to find the components of that gravitational force. So the components are two. We have the vertical components. The vertical component, which is force of gravity vertical. It is that one which is in the same line with the normal force. The second component is this one, which is the parallel component. Is parallel to what? Is parallel to the surface. So that means both of these components are relative to the surface. So that means we have force of gravity parallel. So just so that it doesn't confuse you guys, we have a surface there, and we are saying we have a force of gravity in that direction. So the components of this force of gravity or weight, they are two. The first one is the vertical, and the second one is the parallel. Vertical to what? Parallel to what? Vertical to this, parallel to this. So let's see. At an at an at at a 90-degree angle. That's what I'm trying to say when I say vertical or a perpendicular to this. I was actually supposed to be saying perpendicular to the surface and again parallel to the surface. So perpendicular, obviously it's in that direction where you have that 90-degree. So this is the normal force. So the component is that one. So you just extend that line. And again, you from that dot there or somewhere anywhere, you can just do another dotted line, but which is parallel to that surface. So this is force of gravity parallel. This is force of gravity perpendicular. Very, very much important, ladies and gentlemen, that you understand that part. Remember, for now, Shriyas, you don't need to stress that much about fully understanding all of this. Just be aware that there's something similar to that. It's going to make a perfect sense when we solve exam type of question papers. Very, very much important, ladies and gentlemen. Guys, before I even go far, LB, are we still on the same page? Are we together, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, 100%. So remember to mute your mic, guys, so that we are all on the same page. So, let's continue. What was I doing, guys? I was trying to derive a formula for calculating the force normal. So obviously, we know that this is actually equals to mg. So what did we say? We said this force of gravity or the weight, it's actually equals to force normal. But you can see that in this case we've got an object which is on an incline. So let me just give you two cases. You have this one which is a horizontal surface, you have an object. So obviously you are going to have force of gravity. Remember, force of gravity is equals to mg, right? So now on the same object you still have normal force. So normal force is that. So what is the formula for normal force? Normal force is the same as that mg, guys. So that is what you should be aware of. That's why we said F, which is force of gravity, it's actually equals to force normal. So we know this thing is the same as the weight. What is the weight, guys? The weight is the mass of an object and its gravitational acceleration. Done. It's simple as that. For a surface which is horizontal, an object being positioned there. Now let's get to the complicated one. So this is where an object is on an incline. So can you see, guys, in this case you have gravity, it's always directly downwards. This one, it doesn't change. So it remains like that at all times. But in this case, can you see the normal force, it cannot be upward in that direction. It has to be perpendicular. It has to form a right angle to that surface. So that means normal force is actually in that direction. And you see, remember, this is a surface which is inclined at a certain angle. So that means you need a Lerato, the components of FG. So that means when you do calculations, you don't consider that FG, but you consider the components for that movement, which is force of gravity, force of gravity parallel. And for this one also, which is force of gravity perpendicular. So I want to quickly try to show you something very, very much important so that you understand where these formulas are coming from. So can you see, guys, I'll just try to make a drawing of a triangle there so that I use trig ratios to explain. Sorry, guys, we've got a vertical line. So this vertical line, it is that one of FG. So what I'm going to do now is to do that perpendicular one,
So we
which is
can't see the
perpendicular
top
to that
part.
line. Okay, let me try to do that. Are you now able to see, guys?
Yes, sir.
Okay, so we had a vertical line which represents a force of gravity. Then this is that first component, which is that of a force of gravity. Force of gravity perpendicular. So now let's do that one, which is force of gravity parallel. So that one for force of gravity parallel, it just has to be a line which is parallel to the horizontal surface. It doesn't matter whether you draw it there. Doesn't matter whether you draw it there, or there, or wherever, as long as it is a line which is just parallel to that surface. So what I'm actually doing now is just to try to derive a triangle where I'm going to use the trig ratios to formulate. So you remember in one of the lessons I asked you guys a question to say, for force parallel, is it FG cos angle or is it FG sine angle? And I also asked the same question for that one. So remember, guys, the angle that is formed is that one over there. So it's more like now we have this triangle. Can you see? This is your hypotenuse. Let me also try to redraw that one so that it makes a sense. So we have this triangle, guys. We have this triangle. You have an angle there. So this is that line from there to there, is that one from there to there. So you have that one up to that one, which is from that one up to there. This is that angle formed, which is angle theta. So an object is somewhere there and it forms all of those vectors. So now this angle, which is I'm drawing over there, it's this angle of that and also that component, and again that component. So I just decided to draw it there. You can see it's just a line which is perpendicular to that. So it forms a 90-degree angle over there. And this angle on that triangle or on this triangle is actually there. So that is why I'm also having it there. So what am I doing, guys? I'm just trying to derive a formula so that you understand where these formulas are coming from. So let's see. Do you still remember, guys, that this line, it actually represents that one of FG parallel? Do you guys still remember? And this one represents that one of FG perpendicular. Do you agree with me on that one?
Yes, sir.
Yes, sir.
100%.
Yes, sir.
So this is the adjacent and this is the opposite to that angle. So that's why it's very, very much important to attend both my maths and physical sciences lessons. So I've done a lot of work on trigonometry. We are almost done with that chapter. So for those of you who missed that chapter, remember, guys, it's not only the general lessons that I'm doing. So just in case if you feel like you either join my group a little bit later or you feel like you've missed a lot and you still need one-on-one lessons, you can just send me an inbox via a Telegram. Then we'll discuss further. So private lessons or one-on-one lessons is those lessons which are not conducted in this group. I've got a special group where I conduct private lessons. So you have an option to either do those lessons in a private lesson where we've got one-on-one, it's just you and the tutor, or otherwise you can still decide to have that in this same group. We had that lesson today with Mr. Sriyas. We're doing functions for trigonometry. So just make sure that when I say we have done this part and you were not part of that lesson, just indicate via inbox. So, ladies and gentlemen, I hope at this point in time you do agree that this side is the opposite and that one is what is it? It's obviously what is it, guys? It's the opposite and this is the adjacent. So which means if this is FG being the hypotenuse, that means for us to calculate the normal force, which is that one, we will need to use trig ratios to derive equations there. I'm not sure, guys, if you would agree with me in saying force normal is then going to be equals to, let's say, what is it? Is it not going to be FG parallel, then cos of angle? And again, for for which one, guys? For this one, which is for parallel. Let's see. A force of gravity parallel. Is it not going to be what is it, guys? Force of gravity. Wait, let me remove that. So it's more like force of gravity perpendicular cause that. And again, let's see, force of gravity. I'm going to remove that. Let me see. Force of gravity is going to be equals to force of gravity parallel sine angle. I'm just trying to think of something, guys. Let me also remove that one and say force of gravity is going to be equals to that. Let's see. Yeah, these are the two formulas, guys, that I wanted to derive. But before I even explain, does it make sense what I'm trying to do over there, guys? Especially for those of you who attended the trig lesson. Does it make sense?
Wait, so why are we using the cos and sine there?
The reason to that is because we are formulating a what is it? We are formulating the components of force of gravity. So we actually have what is it? We have two components, which is that one for parallel, and again we have that one over there. So let me quickly try to do this. Maybe it might make sense. Let's try to derive trig ratios, or maybe assign this using trig ratios. And the first trig ratio, let's say cos angle. What will cos angle be equals to? So cos angle is going to be equals to what is it again, guys? Cos is adjacent
Adjacent over
over.
hypotenuse.
Yeah, so what is adjacent there? Adjacent, is it not FG perpendicular? It is FG perpendicular over FG. So we cross multiply, which means a FG perpendicular, it's equals to what is it? It's going to be equals to F of G multiplied by cos of angle. Then we do the same for sine. We say sine angle is equals to, what is, guys? What is the trig ratio for sine?
Opposite over hypotenuse.
What is opposite in this case?
FG parallel.
So it's FG parallel over hypotenuse being FG. Then you cross multiply, which means FG parallel is equals to FG sine angle. So guys, I just wanted you to be aware of these two formulas. Then at the later stage, we will use these formulas. But for now, you don't need to worry much about trying to derive all of that and everything. Just be aware that we've got this type of a formula and that one. Then we'll use those when we perform some calculations. So between these two formulas, which one is for the normal force, or which one can be worked out with the normal force?
FG perpendicular. A.
100%. So that means I'm going to talk more about that one for A. So that means, do you agree that force normal, which is a vector quantity, is equals to force of gravity perpendicular? Do you agree with me on that one?
Yes, sir.
And again, do you agree that FG perpendicular is equals to force of gravity cos of angle. And again, do you agree that force of gravity is actually equals to mg? Then you still have cos of angle. So this is the final formula. So that means force normal is actually equals to that. And remember that the whole of this, it's a component on an inclined surface. So guys, just be careful of that formula. I'm going to teach you on how to apply that formula in all the situations. So we'll just be using a formula with a trig ratio. So on an object which is on a horizontal surface and again on an inclined, will just remain constant or remain consistent in using that type of a formula. So now, if we talk about the kinetic friction, so that means friction kinetic is going to be equals to mu k multiplied by a force of normal that. So I think, Lerato, you are in grade 11 and everyone else was in grade 11. You use this formula somewhere, somehow. I'm just making an assumption.
So we
I
can't see the
hope,
bottom part.
let me do that. Are you now able to see?
Yes, sir.
100%. So I was saying F-A-K, which is what did we say is that is the kinetic coefficient of friction. It's equals to mu a kinetic multiplied by force of normal. So remember, force of normal, it could be gravel, it could be tar, it could be a ceiling, it could be ice. This one, it tells the roughness of this material. So you should use this formula that much. But otherwise, let's now try to continue with our lesson for today. So that's all that I wanted to explain with regards to a frictional force. So don't worry that much about all that I explained. It will make a perfect sense as we continue. Ladies and gentlemen, a very quick one. Let's quickly talk about applied forces. So this is the fourth type of force that we'll be looking at. So obviously, guys, how do we represent an applied force? So an applied force, obviously, we talk about Fa. So with this type of a force, ladies and gentlemen, we are talking about two simple things: push or pull. Easy, 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 easy. So we just focus on two things, guys: push or pull. So that song of push, 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 push mahurumeja, what, guys, you just sing that song, not noticing that you are actually talking about something that you'll be asked about in exam. So it's either you push mahurumeja, or you pull. Easy, 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 guys. An applied force is a force that a person, not necessarily a person, it could be an object, that applies to another object. It's as easy as that. That is the explanation of an applied force. Ladies and gentlemen, an applied force, it's a force that a person or an object applies to another object. That means we're talking about two objects. The other one has to apply a force on the other object. And that other one could be a person, or it could be another object. So if a person, for example, is pushing a cart along the ground, then there is an applied force acting upon the object. Let me quickly represent that. Let's say we've got a card there. Let me just check who is in this group. I see Kevin. So here we've got Kevin, ladies and gentlemen. He's pushing that cart. So now, very, very much important, ladies and gentlemen, already I'm able to notice that we have force being applied. Where is Kevin applying the force? He's applying the force directly there in that direction. So this arrow represents applied force. What is he doing? Is he pushing? Is he pulling? Guys, Kevin is pushing. Easy, 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 easy. Already, I'm able to notice that we might potentially have other forces. What other forces are we having, guys, over there, apart from a applied force?
A frictional force.
Frictional force.
Frictional force.
Normal force.
Frictional force, normal force,
Weight of an object.
Gravity.
weight of an object. Ladies and gentlemen, very, very much important that at all times when you're looking at an object, you are able to visualize possible forces. So guys, that's all that I had to say with regards to an applied force. Nothing complicated there, nothing, confusing over there. Quickly, let's talk about the last force or the last type of a force, which we call tension. How do we represent tension, ladies and gentlemen? You can just say capital letter T there, an arrow to show tension. It's a vector quantity, or you can just use capital letter T
So you
over
can't
there.
see the top part.
Sorry about that. Are you able to see now?
Yes.
Kind of, but not clearly.
Let me move it again. Is it clear now?
Yes, sir.
Okay, 100%. So guys, when an object is pulled by a rope, not necessarily a rope, it could also be a string or a cable. So when an object is being pulled by either a rope, string, or cable, or hanging from a ceiling, very, very much important, ladies and gentlemen, the rope or whatever object it is applies a force on the object. So let's say there's a ceiling. Then we have a rope. And then we've got, let's say, an object. So this object is being pulled by, in physical sciences, they can say a rope of negligible mass. Otherwise, they can say a string. So just be careful of the type of words which they normally use in physical sciences. Otherwise, they could say it's a cable. So this is hanging from a ceiling, ladies and gentlemen. Doesn't matter whether it's double L there or whatever. I know you know the spelling, the correct spelling. So this thing is hanging from a ceiling. So it's being pulled by rope, string, or that. Guys, this rope or this string or this cable applies a force on the object. Here comes a question. What is that force called?
Tension.
100%. That force is called tension, which is what I'm explaining in this case. So guys, it is a contact force and it acts in the opposite direction to the pull. So obviously, um, if an object hangs from a rope, the direction of the tension is always upwards in the rope. So this object is obviously being pulled by something. Guys, are you able to identify additional possible forces over there? And which one is it?
Yes, sir.
Weight.
Wait, sir.
Wait.
100%. So we've got the weight over there, or otherwise force of gravity. 100%, ladies and gentlemen. So that means the tension in the rope is in the upwards direction, and this thing is being pulled downwards towards the center of the earth. Very, very much important, ladies and gentlemen. Nothing complicated over there. That's all that I wanted to talk about in relation to the tension. So I'm going to remove all of this and talk about something very, very much important, guys. Very, very much important. Force diagrams and free body diagram. These are the two things that I want to talk about. So, force diagram and free body diagram. You need to be able to distinguish the difference between the two. When the question says draw a free body diagram, you should know exactly what you're supposed to do. When the question says draw a free body diagram or the force diagram, you should know exactly what you're supposed to do. So in force and free body diagrams, we consider forces acting on one or the same object. Does it make sense, guys? Just so that we are all on the same page. Let's say we've got a ball, and again we've got a wall. Maybe this is a ball which is being hit in that direction to hit that wall. So listen to this very carefully. In both force and free body diagram, ladies and gentlemen, we consider forces acting on one object. Does it make sense, guys?
Yes, sir.
So that means if we draw a force diagram or free body diagram, it's either we draw for that object or for that object, and not for both at once. So when you answer questions about force, you must, ladies and gentlemen, do the following. Very, very much important. The first thing, name the forces. Very, very much important, ladies and gentlemen. Name the forces. Secondly, state which object exerts a force on which object. Very, very much important, ladies and gentlemen. Which object exerts a force on which object? A force on which object? Lastly, state the direction of the force. Direction of the force. Very, very much important, ladies and gentlemen, that you take into account all of that information, because otherwise we won't give what examiner wants. Guys, a very quick example that I would like for us to quickly do. Akona, make sure to mute your mic. Akona, make sure to mute your mic. There's someone that I muted their mic in this group. Let me just quickly check and see if I can unmute. Okay, she's out. Akona, mute your mic. Akona, mute your mic. So I'll just give the last chance to mute your mic. So guys, a very quick example. A man pushes. You can just write it down. A man pushes a loaded trolley. Someone mute their mic along a horizontal floor. So this is a quick example that I want us to consider. So that means this is what we have, and we've got a man who's actually pushing. Let me put this man on this side of that loaded trolley. So I might need to just redraw all of that trolley. Yeah, it's a loaded trolley with some whatever objects there. So here's the man who's pushing that trolley. So obviously, guys, we can identify the following forces that are acting on the trolley. Can you see, guys, the forces that we're identifying, where are they acting based on what I've said? I'm saying we can identify forces acting on the trolley. So when I draw, or when you draw a force diagram or a free body diagram, you will be drawing forces acting on what? Will it be on the trolley or on the man?
On the trolley.
The trolley.
100% on the trolley. So the applied force, obviously, which is being applied by the man who is pushing, you start drawing it from there where the hands are. Then you draw it in that direction and you call it applied force. Very, very much important, ladies and gentlemen. Obviously, there is possibly a frictional force. So this is where you draw that frictional force. Remember, these are vector quantities. You obviously have a normal force. So that normal force, you start it from the surface, because this is the surface which is exerting a normal force. So you don't just start a force anywhere you like, guys. Be careful of that. And then the weight, very, very much important. The weight starts from the center of the object in the direction of the downwards. So you don't just anywhere draw those forces. Guys, does it make sense to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, 100%. Guys, forces acting on an object can be represented by force diagram or free body diagram. This is what I'm actually explaining here, guys. Remember, the head of this part of explanation is based on force diagram and a free body diagram. So let's talk a little bit more about, maybe let's start with force diagram. So you can just write all of this as part of your notes. So force diagram. Guys, the object is represented as a block and the vector forces as vectors. So that means, firstly, you represent it as a block. And what does the block represent? An object. Very much important, ladies and gentlemen. So the vectors start at the point of application. So that is basically what I was explaining before I removed all of that. So the force starts at the point of application. Force starts at point of application. And lastly, weight is drawn from the center of gravity downwards. So weight, you draw it from the center of what? Of that block. Guys, let's talk about free body diagram. So, Kevin, most of these things, you just need to be aware of that. It will make sense when we try to do a drawing. So, firstly, guys, the object is represented by a dot. Very, very much important, ladies and gentlemen. It's represented by a dot. What does the dot represent? It represents an object. Very, very much important, ladies and gentlemen. The vectors start at the dot and they all point away from the dot. So that means the vectors, they radiate from the dot and move away from the dot. So you just need to be aware of that. It doesn't matter how you write it, as long as you can still remember that in a free body diagram, we represent the object by a dot, and we have vectors radiating away from the dot. So if the object is on an inclined surface, the weight vector can be resolved into two components. So you remember, guys, let me say weight converted into components. So with regards to these two diagrams, guys, and also the calculations, it's easy when we deal with an object which is on a horizontal surface as compared to an object which is on an incline. So the only funny thing here is that you've got two components. So this is the weight. So what
So you
makes it
can
a
see the
little bit
bottom part.
okay, let me do that. Thanks for that. Are you now able to see?
Yes, sir.
100%. So saying the weight, it has the components on an inclined surface. So I was saying it's easy when we deal with an object resting on a horizontal surface as compared to on a surface which is on an incline, because you've got components there, and these are the two components, which is FG perpendicular. We know this one. What was it? Was it FG sine or was it cos? I think this one it was cos angle. Just make sure that I'm correct on that one. And this one, if I remember, I think what was it, guys? What was it, guys? I think it was FG being equals to
Cos.
oh yes, this one it was for cos. So it's what is it? FG cos of angle, 100%. So this is the one where you might need to be a little bit more careful when you solve, especially in cases of calculations. So I just want to quickly take you through those diagrams. Let's just try to quickly make some drawings. Then you will tell which drawing is which. I hope you'll be able to see over there. So this is what I'm going to do, guys. I'm going to have that. I'm going to have that. I'm going to have this. Let me actually do this, guys. Let me actually do this and draw that, which is there and there. Then I've got that, which is FG vector, and then again I'm having that, which is F normal. So is this a free body diagram or a force diagram, and why?
Force diagram, because it is indicated by a block.
It's a free body diagram because it's represented by dots.
Guys, is it a free body diagram or is it a force diagram?
It's a force diagram, sir.
A force diagram.
It's a force diagram.
So maybe Lerato, let me say I actually wanted to draw a force diagram. So that dot over there, you might be having a point, but in my mind, I made that point just to show that when it comes to force of gravity, it actually starts from the center of that object. So let's say, for argument's sake, in case if a question comes, then it's just going to be something drawn like that, and maybe another one drawn like that, and they're going to ask if this is a force or free body diagram. But in most cases, they won't ask you if that is this or this. They're just going to specify to say draw a force diagram. So you just need to be aware that you represent it by a block. So obviously that one is going to be what is it? It's going to be a force, a free body diagram. Yes, someone is asking a question.
Say for force diagram, is it wrong when I write normal force on top of the box?
Are you asking if maybe you draw it like that, or
The force diagram.
so you are asking if you draw it like that, ne? So I'm just going to make an assumption that it's a yes. So guys, remember, what is exerting a force on the object? Is it that part or is it the surface?
The surface.
The surface.
So if it's the surface, then start your force from the surface all the way up, so that it's clear that it is the surface which is exerting an upward force on the object. Lerato, are you happy with that explanation?
So it's not Lerato who is asking, it's Moleboheng.
Oh, Moleboheng. Lerato's sister, is it Lerato? Is it you?
Lerato's sister, sir.
Okay. Yeah, and I think you've got almost the same. You sound the same, so it's fine. So Moleboheng, it has to start from there, and be careful when it comes to the weight. It starts from the center of the object vertically downward. So you must also show an arrow. So guys, I just want to show you something very interesting, guys. Very, very interesting. This is going to blow your mind. Let's say we've got an object on okay, let me just draw this. Let's draw a free body diagram for that object. So obviously we represent it by a dot. We make a vertical line, and then from there I draw that, and again I draw let's say that. Here comes a question, guys. Is there someone who can guess which one is the applied force and which one is the frictional force?
So we can't
Sir,
guess.
Frictional force is the one on the left hand side.
Remember to
Can't
give your
guess
answer
because
for every comment that you make.
we can't guess, sir.
Moleboheng says we can't guess. Is there someone who says we can guess it? And if we can guess, what is your guess?
Frictional force is the one on the left hand side.
Remember to give a reason to your guess, guys. Whatever guess that you come up with, remember to give a reasoning behind that. So I'm just going to give you guys some time to quickly think about it. And then from there, I'm going to give you an explanation a little bit later. So, guys, quickly think about this. Just look deep into that and try to tell if we can guess which one is the frictional force, which one is the applied force, and again, which one is the normal force, which one is the weight. For every answer that you give an answer to that. I'm going to start with Moleboheng. Moleboheng, you're saying we cannot guess. Tell me why we cannot guess. The other one who guessed, tell me why you go with your guess.
we are given the object and the surface. So the arrow that is pointing upward is the normal force, and pointing down is FG. We are not told that the object is moving to which direction.
Lerato, you made a perfect point which makes sense. I'm not saying it's wrong or it's correct. So the next one to give it a guess. I think it was Kevin who tried to give it a guess. Who was speaking or who was making comment on that one, guys? Who was it?
Same as her. I don't know which direction does the box go.
Okay. Guys, thanks very much for your input. I'm now going to say something which is very, very much important. Take into account the length of that arrow. Take into account the length of that arrow. Between length A and length B, which one is bigger or is longer?
Length
B.
B.
Which means we are most likely to have force of friction in that direction. I mean, applied force and force of friction in that direction. Makes sense?
Yes, sir.
So here
So
comes the
may
question.
I ask,
Mm-hmm.
with force applied, you said it's either push or pull, right?
Yes.
And looking at this diagram there, we don't see anything that pushes or pulls the object. Therefore, it's like stationary. So I'm confused with the force applied.
So remember, the reason why I did not draw a Kevin pushing is because if Kevin was on this side, you were going to know that, okay, the applied force is in that direction. So that's why I was saying just take a guess in terms of which side could possibly be an applied force and which one could possibly be the frictional force. So the main point that I'm trying to make out of this, guys, is for you to notice the length of the applied force and the frictional force. So whoever who made that comment, it's a very good comment, but remember, based on what I've said, that's why I mentioned the word to say, by just looking at that free body diagram, which arrow could possibly be that of applied force and which one could possibly be that of frictional force. So I wanted you to imagine Kevin pushing, but I did not want to draw Kevin there because if I draw him on this side, possibly with his hands, you might assume that he's pushing in that direction. So I could have still drawn him, but still with his hands, he can still pull. But what I actually wanted to emphasize in this case, it was just the length of these arrows. So that means now that Kevin is pushing, if you were to draw a free body diagram there, make sure that now that you know he's pushing in that direction, then you make this line a little bit longer than that one. Why longer? Because here you show is the applied force, which means this thing, it's now moving and it's moving in that direction. So this one is going to be a smaller force which is resisting that direction. So guys, notice we are having equal lengths there. But before I proceed, are you happy with that clarification?
Yes, sir.
100%. So guys, we are
Yes,
having
sir.
a same distance over there. What is the reason to that?
It's because the object is under surface.
She says it's because the object is on the surface. Anyone else to give it a try? So, this is the reason, guys. Remember, Lerato. Let's see. Here we are talking about forces. So,
I think the two forces are acting on the object.
she
I
thinks the
think the
two
two forces are
objects
acting on the object.
are acting on the objects. Thanks for that input. So here it's an explanation, guys. So of course we are talking about the forces, but the reason to that is because these two forces are the same. Not necessarily that the two forces are acting on the object, because even these two forces are acting on the object, but the arrows are not equal. The reason to that is because, remember, force normal is equals to force of gravity, but in the opposite direction. That is why when you formulate...
Can you please repeat the question?
The question is already answered. I'm not sure. Okay, let me still ask the question, but you don't have to respond. So the question was, why are we having equal arrows in that direction and that direction? Why is it that those two arrows are equal? So the reason to that is because the forces are equal. So I was saying, if you remember, when you say force net, we talk about the total forces acting on an object. What are those? Remember, all of these forces are vector quantities. So they therefore have the direction and the magnitude. So let's see. Maybe we can say the first one is applied force and assume to the right as positive. And again, which means left is negative. And up, we can assume it to be positive, and down we can assume it to be negative. It doesn't matter whether you choose otherwise. So let's see. Applied force is going to be positive force applied. Let's see. What about the frictional force? It's in the opposite direction. It's going to be minus. What is it? It's going to be minus a frictional force. But when it comes to the normal force, remember, a normal force it's in the upwards direction. So maybe normal force, if it was 40, then it means even G is still 40, but in the opposite direction. So that is the reason why when we deal with force net, you exclude those two from the formula, is because on their own, they cancel each other out. You therefore remain with applied force and frictional force. Does it make sense, guys? For those of you, especially those who are upgrading, because you've done this chapter and also the calculations. Does it make sense?
Yes, sir.
Yes, sir.
So, guys, are we all on the same page?
Yes, sir.
Yes, sir.
100%. So now, let's have a look at something very, 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 very much important. I'll just remove all of this. And then from there, I'm going to quickly indicate the four symbols in diagrams. Very, very much important, ladies and gentlemen. So we use these symbols to help represent forces in force diagram and free body diagrams. Very, very much important, ladies and gentlemen. So the first one, you can consider force. It's a vector quantity, or otherwise you can represent it as force applied. So this is when you represent an applied force on a force diagram, or otherwise on a free body diagram. Makes sense? The second one that I want to talk about is the frictional force. So you can represent the frictional force in that way, or otherwise you can just represent it as capital letter, not really a capital letter F, but just a small letter f, because if it's capital letter F, it therefore looks the same as an applied force. So it's just a small letter F, but a bigger version of it. So the other type of a force which could potentially be a part of your answer when you draw a force diagram or a free body diagram is the frictional force. No, the gravitational force, because this is the frictional force. Or you can represent it as the weight. The other one, obviously, is the normal force. Or otherwise, you can represent it as just N. And the last one, ladies and gentlemen, it's the tension with an arrow there. And then you say O, T, which is capital letter T, which means the tension. Guys, does it make sense for everyone?
Yes, sir.
So quickly, I'm going to explain for each of those forces. So obviously, FA, it's an applied force in the direction applied. Secondly, we've got frictional force, which is the surface on the object in the opposite direction to the motion. The third one, we've got gravitational force or weight, which is a force exerted by the earth on the object. And obviously, we know it's always downwards. So Fn, it represents the normal force, which is the surface on the object. And remember, perpendicularly upwards from the surface. And lastly, guys, we've got the tension, which could result from a cable or a rope on object in direction of motion. So these are 1, 2, 3, 4, 5 forces which you may possibly have or have to indicate when you draw a free body diagram or a force diagram. Make sense, ladies and gentlemen? Does it make sense to everyone?
Yes, sir.
Guys, does it make sense to everyone?
Sir.
If that is the case, guys, I think this should bring us to the end of our lesson for today, of which I assume you enjoyed as much as I did. And guys, I'm hoping to see you on our next lesson where we'll be doing some calculations. So because some of you guys are in grade 11 or otherwise, some of you guys are in grade 12. So for those of you who are in grade 10, you don't need to worry that much about the lessons where we'll be doing some calculations. But remember, you are still welcome to join just for exposure. But those calculations are not really directed to the grade 10 learners. So guys, grade 11s and grade 12s, did you guys really understand what was explained in today's lesson?
Yes, sir, we did.
Yes, sir.
Sir.
Because today's lesson was, it was a very important lesson because all the calculations that we'll be doing on this chapter of work, energy, and power are based on this lesson. So that is why I would say consider yourself lucky if you attended this lesson until the end, because when we'll be doing the calculations, you will never and you won't get lost. So I'm thinking on upcoming lessons, what we should be doing is to straight away work on exam question papers. What do you think, Lerat? TK, Kevin, Tando, what do you guys think?
Yes, I would really appreciate it.
Yeah, we
I
can
see
read
we
them
have
questions, sir.
Young, Minentle, Akona, TK, Moleboheng, Zitebatso, Koketso. So next lesson, we rock question papers, isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, 100%. So just make sure that you don't miss those lessons. So guys, this brings us to the end of our lesson for today, and thanks very much for joining. I'm hoping to see all of you guys on my next lesson. Have a very good night, guys.
Thank
Sir.
you.